Good evening, everybody. I think we're live now. So, welcome to the MakerCast, episode 38, if I'm not mistaken. What is the MakerCast? It's a monthly show, hopping from channel to channel on the first Sunday. Basically, we talk about what we've been up to and what we're going to do maybe over the last period of time. And people that are new to the show have a wild card. So, Matt, you can show whatever you want, and we'll just be surprised. My name is Mark, electronic engineer, and today's guests are fastest ultrasonic U-boat, bitluni. Recovered from illness, Dave Darko.
I was sick.
He was actually supposed to be on the last show, but he got sick the last minute, so
Yeah,
making up for that today.
some back stuff.
And we have the man who always has a rubber dog as house pet. That's Meyer. Clem.
Hello.
And we have Matt Venn participating for the very first time. Welcome, Matt. And last but not least, we have Radomir Tupiranski. I hope I pronounced that right. Also known as deshipu. I'm happy to say that he has more color in his webcam than on his Discord profile photo. So before we start sharing our latest work, I want our viewers to get an idea about who we are. So I will ask everybody to just say in a short sentence or a very short story, what was your main occupation last year? What kept you busy, rather on YouTube or in your business life? Dave, can you start? What's your job? What's your occupation?
Yeah,
This is already the
Where have you been?
Is this already the quiz? I'm not prepared. So we're talking about the year or the month that we let in?
Yeah,
Okay.
just in general. Give
Yeah.
us an idea. What is your profession? What do you do?
Okay.
So that people know. What's your background?
I'm sorry. I was just getting this in the chat from YouTube in another window. But anyways, I was distracted. I'm so sorry. I'm here. I'm Dave Darko. I like to share, sometimes artsy 3D prints, sometimes cool PCB designs that involve either, I don't know, sometimes an ESP, sometimes it's just analog stuff that makes some beeping noises. And yeah, that's
Okay.
me.
So basically electronics.
Stuff.
Okay. Matthias, bitluni, how about you?
Okay, so what did I do last year? I tried to do YouTube. As some people say, I'm a wannabe YouTube maker. I really can't remember. That's all. That's my profession. So
Okay.
that's my and yeah. There was nothing else last year.
Yeah, that's good.
I'm
That's
sitting
okay.
in my basement.
Clem, how about you?
Yeah. Hi, I'm Clem. I make videos for a channel called Element 14 Presents, which is 99% about electronics. And I've used to be more into 3D printing, and now I'm like selling 3D printing resin and stuff as my part of my business stuff. We will hear something about something new today.
You're going to smash something today again?
Oh no, maybe I can smash one thing.
Because usually every episode you start pounding around your products that you make with your resin and hammer it down until it's broken, and usually it doesn't break. So
Something to crash.
okay, Matt, how about you?
Yeah, hi. Over the last year, I've learned how to make computer chips. So that's been my all-consuming adventure over the last year.
Okay, gotta go now.
Yeah. So that's
Okay, good.
that's what I'll show. I'll show one of the chips that I've made and try to explain
nice.
the process.
Okay, good. Deshipu.
So basically, my latest obsession is ergonomic keyboards. So this is a couple of them. That's I made previously I made some game consoles, so I'm going to show that as well. And before that, I don't remember. Generally, game consoles and keyboards. And I don't have a YouTube, really. I share everything on hackaday.io. So that's fine.
Also do robots sometimes. Pretty
Yeah,
cool.
robots were like 3 years ago. I have one still waiting here for finishing, but I don't really have the energy for it. Maybe when the spring comes, it comes alive then.
Okay, good. And before we start showing off what we've been up to, there's one more thing I need to remind you guys of, and that's this one, because we will end the show with a little quiz. And maybe unlike before, I'm not sure if it's been done before, but not the last episode. This time, all viewers can participate in the quiz. In the end, I will show this link again. It's WooClap, and with this code, you can participate in the quiz. And the quiz, you can open it already, and it's just theirs for later. Instead of being bypassed, you can just participate. So, but that's for later. Right now, we're going to start with Meyer.
And he's gone.
Oh, no, I'm here. And now I'm gone.
Well, I'm trying to make him big
Just
screen.
drag him over. Just take him by the hair and then put him on top of you.
Put me somewhere.
Put you somewhere.
Okay, now I'm somewhere. Hello?
Oh, you're somewhere. Going to make you big.
Okay.
Yay.
So, ladies and gentlemen, what I have been up to is, do you want to start with the 3D printing stuff or with the electronic stuff first?
Electronics?
Electronics.
Because you're holding the resin.
Yeah. Okay, so electronics-wise, I have made this little thingy here. And currently version number 2 or revision number 2 is in PCB production. I hope it's halfway decent now. It's called US Bitch because it makes USB your bitch. I have asked Brian Locke for permission to iterate on his power blocker, the almighty thing that strips out the power lines from your USB connection when you connect it to your 3D printer so the display doesn't stay on when you're using Octoprint. And for whatever purpose you want, maybe you just want a data connection for debugging because your thing is already powered another way and you don't want to have like issues with that, which can happen. Also, it's handy when you are trying to build circuits with like microcontrollers like the ESP32S2 because it has native USB and you have a secondary UART connection on there. And when they are both like entering power, that may give you some glitches. So that's handy. But I thought, yeah, and then sometimes I want to have no data and sometimes I want to have no power. And I don't want to switch devices all the time. So I made a thing that can do both. So you plug in your USB cable in here and then it goes into your computer or whatever. And you have little jumpers and you can set them to all the possible combinations. So you can, if you change the red one to the other thing, then you have no power. And you can also change like the data connection. So no data is also possible. And on these pins, you of course can also add some wires and get that connection to your breadboard. So in case you want to sniff USB or you just use this as like the USB plug for the device you're building, then you have it. And also it has some LEDs so you know on which sides of this connector power is present. Because sometimes you want to know if your device is maybe actually not really powered up while debugging until you actually realize that the connection is not there because there's no power. And also, in case you don't want it to be externally powered, then you know what's up with it. So yeah, that's the thing. I'm currently having the second version in production that has some very obvious change. As you can see, this connector is on the wrong side. Yeah, and the next revision, this one is on the right side. That's pretty much all the changes. And yeah, it's called US Bitch, and I've like ordered 10 of these, and I will put them on my Electron store if somebody's interested. Yeah.
I hope there's gonna be a revision and the name is changed.
Why would I change the name?
The comments are like, oh god, oh no. Okay, one of them is mine, but there are people.
I just got demonetized with what you said.
That's like.
What's to know about that? It even has an asterisk. It's not even written fully.
Go with the times, Clem, please.
Yeah. Everybody. Okay, let's do the other thing. You want to see stuff smashed. So, as a lot of people know, I have my own resin, which is like crazy strong and stuff. And there are also like a lot of people have experimented previously with mixing stuff into resin, like hard stuff, powders, glitter, and other stuff that they want to embed in the print. So you get like sparkly, nice looking prints like you could do with filament that has like glitter in them, which looks really nice. I actually have here, like, this is a little games console I made a while back, and it has like glitter filament on the case. So that looks pretty cool. And now I'm me. So I hope people still see that. But that's like glittery, and that looks pretty nice. And yeah, for years people are trying to make that with resin, but it always has the same problems that you put resin in, you put the glitter in the resin, and it just sinks to the bottom. And then yeah, when you finish a 3D print, it's like a little bit of glitter on the first few layers, and then it's basically nothing because all the glitter just sinks to the bottom and doesn't suspend really much into the material. But it happens.
But isn't the bottom where all the glitter sits and where it prints also? So shouldn't it be full of glitter? That's weird.
Yeah, but the part that really has like a lot of glitter usually is like the first few layers, and then it gets thinner and thinner and thinner.
Okay.
So it pushes it to the side, and it just sits on the edges. So it's not uniform.
Also, doesn't glitter block out the light that is supposed to cure the resin?
Yes. Also, and it scatters it. So yeah, that's a lot of problems. There is a pretty popular video by Tom Sandladerer who tried out different materials, and it's basically always the same outcome. So this stuff is a lot more viscous than normal resin. So I thought, hey, maybe the specific weight of this is 1.18 kilos per liter. And I thought, maybe that's enough to keep the stuff suspended for longer. So I tried that a few, like 1.5 hours ago. And we have prints, and I hope it's just get more light. Maybe it's visible, but there is actual glitter in this print. Maybe make me bigger so we can see them. Trying to get, doesn't like focusing that close. Okay, as you maybe are able to tell, these are like little hooks that have glitter in them, and it's pretty equally suspended, but that's just like a little bit of glitter. And it's still, that's one of my main concerns, is still like really hard to break, and that's like 2 millimeters thin. So
and there we go, breaking stuff.
Yeah. And then we have like, this is just like a few layers because I didn't have much longer time, but it's like the maximum amount of glitter you can get into a print. And it's more than 50% of it, like in this area, like chock full of glitter. And now I'm like, I'm trying out how much glitter can you put into that until the print fails. I can tell you now that's like a lot more than in a normal, more liquid resin, but I haven't found like the right mixture yet. Yeah, and when I get that mixture right, I have done it 50-50, and now I'm diluting until it works again, because I thought it's easier to measure the big amount. Yeah, now you can probably see it better. It's like, oh, come on. Ah, God. Okay, this is probably the best one I get.
Now we can see.
Yeah, okay, so that's like pretty much solid glitter in there. That's like 50%. And then it fails after a few layers, and now I'm diluting to get to the max amount of glitter that you can put in. And I started at the biggest amount because that's a lot easier to measure when you have like very light stuff than measuring the tiny amounts and adding them up, and you always have like losses in there. So I'm starting at the bigger one and then dilute, and I can pretty much measure that by weight to know how much glitter I can put in a resin until it fails printing. I've tried, it stays in there for about an hour until it starts really like visibly sinking. But that's like, I don't know how much longer than usual, but it's a lot longer than usual. And yeah, I'm currently trying that out. The next thing after glitter, and I've already prepared that, is like volcanic, how is it called? Volcanic dust. Like when you have very fine powder made of volcanic stone. Yeah. Any case, that's the next material I'm going to try. Why? Because I've used that together with epoxy resins, and if you mix that in and make a layer, that's you can't even like sand it anymore. It gets extremely tough, and I want to try out how much of that could I add in and have it still 3D printable, because that would be quite interesting if that works. And now for the show element that you've all been waiting for, I have here two raspberries.
Smash it.
Yeah, so I think it should make me bigger so people can see. So this thing is a Raspberry Pi case. They're both like pretty shitty prints. So I'm not like concerned with smashing them. This is normal standard resin, blue type, and this is this stuff. Okay, let's. Who wants to give the commando? Let's do it like that.
Just go.
Just go.
Just do it.
Okay. So that's
That was one day of printing.
That's how normal resin is. Here's a case, other stuff.
Nice.
Still
Take
fine.
a hammer.
Don't hurt yourself.
Yeah. Oh,
No need
gone
of
for the
bondage.
Ouch. I
First aid kit, please. Someone bring the first aid kit. He's wounded.
Turn down your
safety
speakers.
sprint.
So
That's an unfortunate placement.
most of the clips are still okay.
it's better.
Okay. So that's the violent demonstration. And if you can imagine, like, injection molded parts would also not withstand that. So,
But by the
There
way,
it
happy
is.
birthday to Raspberry Pi, 10 years. Woohoo!
oh yeah,
Wow.
happy Raspberry Pi
Happy
Day.
birthday.
I should make some new cases.
Glenn, there's a question from David Watts. Does it have fibers in it to make it stronger?
No, it does not. I would like to
Okay.
try out fibers, but the problem with fibers is that when you have some that are short enough that they are good 3D printable, and don't like clump up, then they don't really have any effect in making it stronger. So they're decorative. And there's also like this suspension problem. So yeah, maybe it's possible with that stuff, but haven't tried that yet. And when you have like long fibers where you can be sure that they have an effect on making it stiffer or more resilient or like give it more tensile strength, then usually you have problems with printing them.
Try asbestos. I heard it's strong.
Yeah, that's for sure strong. Yeah,
Okay.
so that's it from me. Hope you had fun. I know I did. And yeah, I'm eager to hear about your projects.
Good. That was nice to see. Dave Darko.
Yay! So I had to. That's me.
Yeah.
So I had to, basically check what I did the last month, or let's say 2 months ago. But there was a lot of things that happened that I posted on Twitter, but totally forgot. For example, these little guys. I just like the colors. I just noticed.
that?
Anyways, these are Scout Oscitones, and one of them is stock. I got it in America and recently sorted it together. And the other one that I have here is a little bit modified. There's like 1 or 2 issues with this board where you can't really run polyphone tunes because those don't have diodes in them.
So it's like a little piano, right? A little keyboard.
Yeah. I should have the power to turn them on. There are always 2 ends to a USB cable. They're pretty cool, and this one, works. I'm so glad about this. Can always do something wrong, and here, for example, I was working on the footprint of the switch to add 2 more pins so I can hook up a diode in there, and there was a 50-50 chance that I draw in the diode the right way. And of course, when I had sorted everything, the keyboard didn't work. So I had to remove all the 20 diodes. And
You can fix that in software.
I technically could, but then I would have to rewrite the software of the Oscitone further. And there's also already a pin swap where you basically switch the timer output with the regular key pin, because this is mixed up in this version. So to get cooler tones out, you had to swap 1 pin. I did that here first, and I had the pins just, there's an Atmega 32.8 in there, or 328 or whatever. It's the dip version, so it has long legs and a big body. And to modify or swap the pins, you can basically just rip them out and then add a little wire and put that in the socket. And that's what I did. But when I was putting it together, the pin shorted again, and it was playing on its own. So that wasn't really what I wanted to do. So I was inspired to just make a new PCB for it, or modify it at least. And the Oscitone Scout, you can basically order all the PCB files. The design files are open source, and also the case files are there. So you can basically get everything into it on your own. But there's like also one issue where if you don't get the 6mm buttons that are 6mm from the case to the button end to the knob, well, then it doesn't really work anymore, because it's resting on the key, or the key thing is resting on the bottom. But yeah, that was still a fun project to do, to source everything and change it a bit. Yeah, and lately I've looked into building stuff for my Eurorack thing again, and I think 2 or 3 years ago I just bought some chips that you can use as an oscillator, and with just a few parts and some sockets, you would be able to put that in a Eurorack. And I've never really done anything with it until I think I started to design something a week ago, and I can probably show that. I want to try the sharing of the monitors because I only have Twitter prepared. Oh, share. That's unique. I've never hit the share button here. Share screen. Let's see which one it shares.
None yet, because I'm supposed to get a notification.
That's true.
It shows up at the bottom in the control room. You need just to take it in, like accept it, like a visitor.
Yeah, that's what I would say.
Oh no. Wait.
I don't think you shared.
Technology.
Does it work? Chrome has lost permission to capture your screen. Follow these steps. Okay, I have to restart Chrome. I'm not going to share my screen. Whoopsie daisy.
Hold up a mirror.
Yeah, let me quickly print something on my black and print. No, but I just show something else. Why not? Yeah, so I made a little speaker Eurorack module, and I basically have this whoop whoop. That's a simple LM386 board that you can get as a DIY kit for €1, I think. And yeah, the speaker is something that I got for the Poly 555, also an Oscitone board, or synthesizer. But yeah, I thought it would be fun to make a little 3D printed panel for it, and it is a 4-color print. So it's white, and then the infill is pink, and then the next layer is transparent, and then there's that's the voodoo form filamentum, I think. But yeah, I was playing around with some shapes, and also had this pink knob that kind of was nice to look at. Surprise. And also, I think I made those in the last 3 weeks, or just sorted them, I guess.
What? Okay.
I didn't design them, and I didn't order anything, but yeah, this is a Turing machine, and a friend of mine was giving me the parts and the panel, the PCBs. I don't know, it's probably also 2 years ago, and this is the VCA and the VCO module from Moritz Klein. He has this wonderful YouTube channel where he explains all how you build a voltage-controlled oscillator, and he has so many videos that are very well researched and explain everything in detail. And at one point, he was contacted by a panel or Eurorack board company, I guess, and they are producing these boards now, which is pretty cool. And I wanted to support the guy, the Moritz Klein person, so I bought the modules, and yeah, happy to have them. What's my plan for this? Well, sometimes I just like to twist some knobs and listen to the weird sounds that it can make. For example, the Turing machine is something where it just randomly spits out voltages, and those voltages you can put in the voltage-controlled oscillator, so it just bleeps and beeps forever in a random pattern. And yeah, that's pretty cool. But I need more oscillators, and I need more low-frequency oscillators, so stuff that just is a bit slower in oscillating, so you can't really hear it, but you can use it as a clock. And yeah, so it's just getting some noises. And
Okay.
I also... Was there, Chris? Okay, sorry. I also bought an electric kazoo recently, and you can just get a thing.
How does that look like?
Let's hear it.
Okay, anyone in the chat wanna guess what the color of the kazoo is?
Pink.
Transparent.
It is. No, it's pink. It came with a green kazoo, but yeah, I also got a pink one and just swapped the kazoos.
Of course.
It sounds like a normal kazoo, but when you connect it to your guitar effects board and turn on the octave and just bring it down, and you're not doing the normal noises that you would do in the kazoo, like the beep, 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 beep. So it resonates, but you're just into it with the octave on. It sounds really, I don't know, out of this world. And I probably have to record this now.
Please.
I don't really have it set up, so I can't really show you what it sounds with the octave, but the normal kazoo is like, I'm sorry, my neighbors. And you can also do, and I can do this thing where I have some oscillation in there. So
That's when you play metal on it.
Yeah, basically. Also overdrive on it. Wonderful. You can use your wah-wah pedal on it. Why not? But yeah. So this is why I'm distracted and not working on my smartwatch. But that thing is, yeah, I'm in contact with someone who offered to help me with the ARM processing and getting started. So when there's more time, I'll get to know how to use the chip that I chose for controlling the LCD stuff. Oh, right. I'm also still working on the Pentagon PCB boards that have the LEDs on it. I'm not gonna play any more tunes. I'm so sorry, but it's 10:30 here, so my neighbors will not like me when I play the kazoo, and they will find me. So yeah, I was the other day I was thinking about what I could do with the leftover PCBs that I have for my what's the shape? Dodecahedron. I'm building an LED dodecahedron right now. But I ordered 15 PCBs, and I don't really need 15. I only need 12 of them. So I thought I could maybe try to make something that's a bit more jewelry-ish. So I have the PCB here with the 51 LEDs on it. And I have this acrylic 5mm plastic plexiglass thing, and there's a foil on it on each side. That's a halfway mirror basically, and this allows for a very thin. I don't know, it's not really thin, but you don't have to use two acrylic sheets and the foil. You can just use the one acrylic piece, and then you get this cool endless mirror effect going.
Nice.
Now we can see your screen reflected in it.
Ooh, So what's
Screen
my
sharing.
favorite icon? Yeah. Oh, let's try Twitter. Yeah, no, you can check my Twitter later. I found a lamp where I printed 3D printed a lampshade for it, and I cleaned it. I, for some reason, scanned the package of a 3D printer and made a little acrylic token of it. Yeah, got that covered. Oh yeah, I made for little shitty add-ons a little thing. You'll find that, and also a little supercluster thing. But I think I showed the supercluster stuff the last time I was on. So yeah.
Very busy.
Any questions?
Wow.
Yeah, but then never so busy that I think, oh yeah, I really managed to get something done this week or this month. Or it's always a distraction from a project is another project, so I'm constantly distracted, I guess. Well,
That's okay if you have time for it. That's what makes it fun.
well, do I? No. But yeah.
Okay.
That's
that's
for
it?
me. Yeah.
Have you
Then,
been following Joey Castillo's work with his
Yes.
PCB replacement
He's-
for that watch?
He's also the reason why I used the chip, and
Okay.
it's totally his fault that I don't have any idea. No, it's really not. But yeah, it's a very good advice. It's an ARM chip with an integrated LCD controller, so I can reuse the LCD display. And
Yeah, and I was
also
following.
managed-
He did this very good, like following down the power consumption, getting lower and lower. That seems like a really important
Yeah.
thing you've got to do for a watch, and it's nice if you can
Yeah.
do it yourself, I suppose.
yeah, I told myself if I can get everything working, then I can start with the power consumption. But before that, there also needs to be a revision already because the keyboard doesn't really work. I can't really tell if I press the upper left button or the down low button because I forgot the diodes. So,
the
yeah.
anti-ghosting.
Yeah, I can put it in every other person's projects, but I forgot it on mine, of course.
You can ask deshipu to help you with the keyboard.
Right. But yeah, I have some
Also,
Okay,
Joey
thank you.
is porting CircuitPython to that chip, so that should make development much easier.
I've heard. Looking forward to that. Yeah.
Okay. Thank you, Dave. And
Sure.
since you started, Matt, why don't you follow? Since you were on screen
Okay.
already, let me make it big.
I'm gonna.
Because I'm very curious about your chip design.
Yes, I got Alan Turing on that side, and my first, my first chip on this side. I'm going to need to share my screen, so let's try to get that working. This one, so you have to give permission, I suppose.
Yeah, I'm trying to find it. I don't see any notification of a screen sharing.
Actually, while we're trying to wait for that, let me just show you the clock. This is the thing I want to talk about. So this is my my new desk clock, over the top desk clock, and the little piece right in the middle is the thing that I've spent the last year making.
Oh, wow.
Let's get
Wow.
the light on that. Yeah. So and then all the rest of it is kind of like infrastructure, and it should have fitted on a little board like this, but we had some pretty serious problems that meant that it became easier to have an FPGA hanging off the side. So it kind of
Cool. I think
doesn't
I
really
know
make
this
sense,
board.
but you know. There we go.
I think this is your screen, isn't it?
Yeah, I got the screen now. Thank you.
Ah, okay,
Yeah.
good.
Yeah, so I wanted to start off with showing the clock, because that's like looking at the big thing. That's like the end result. But then I've got like this great opportunity to now show you all the way down the layers right until we get to the absolute tiniest parts in the chip. So in January, I got sent these little boxes full of chips. I got there's 200 in each one. So for all you people suffering with the chip shortage, I got I got 600 right here. 400 of them were bumped. They're like little BGA packages, and we had to solder them onto like a breakout board, and this is provided by eFabless. And because of the problems, we were getting about 40% were working at all. So I soldered up 10, and then out of them, like 3 or 4 were able to load some configuration. And 200 of the chips. Oh, now I'm full screening. I'll show you these. So that's like the breakout board, and I also been playing around with trying to suspend chips in epoxy. So I was kind of interested in what you were showing earlier, Clem, but I think this is the 2-part resin. So you pour the stuff in. Yep. So working on trying to get the bubbles out of that to get some
So Matt,
nice things.
this chip you designed, it's for a clock, you say?
It's got 9 designs on it, and one of the designs is a clock.
But is this as kind of a showcase? Because I can imagine
Yeah,
you
it's
want to
like
do some other stuff with this.
Yeah, it's a good question. It was more for learning rather than for
Okay.
like making something that I could sell. Yeah.
Yeah, clear.
Okay. Yeah. If you put me the screen share on again. Okay, and then I put together an info pack here, which is public. It's maybe I'll drop the thing in the chat. It's bit.ly mpw1 samples. Maybe someone could copy that into the YouTube thing. So then we've seen that level of the chip, these little things you can hold in your hands, and then I got a guy called Olivier volunteered to do some scanning for me, this is the bare die, so you can now see kind of a little bit closer in. This is 5mm by 3mm, and he was also able to strip off the top level of the metal, so you can now see down and see my design. So this part is a little RISC-V processor and 2 kilobytes of memory, and then these 8 blocks here are the kind of actual designs, and I think it is this one here, that is the VGA clock. So we're going to keep zooming down into that. So I'll bring up my terminal now. So this is the file that I sent to eFabless in like January last year. Where is it? There. Okay.
You had this presentation on the SuperCon, didn't you?
Yes. Yeah.
Yeah, that was fascinating. I was watching it live. Yeah.
Yeah. On the most recent SuperCon, I was doing like a year's worth of retrospective, so covering a lot of things. And this time I thought I'd just focus on this one thing, this clock. So I think that's, oh, there it is, it's this one. So now if we zoom in to here, you start seeing more of the details. You can see like the individual wiring and the logic that makes it up. If I click on this, it tells me down here what the type of cell it is. And it's a flip-flop.
How many layers are these?
There's all these ones on the right-hand side you can see here. But there's about 40 layers. But it's for people that are familiar with like PCBs, it's quite like that. And you send those layers off to a factory, and then they put it together into these into the actual finished chip. So drawing and wiring this, so we've got 5 layers of metal that we can use for routing, and then like 3 or 4 layers of the active stuff that build the actual working transistors. But we don't draw this out ourselves because that would take way too long. So instead, we use, if I don't know if anyone's done any FPGA stuff, it's a little bit like coding, but it's got some differences to it. If I run this command, this shows you after I take my hardware design language, which is Verilog, and I run it through Yosis, which is the open source synthesis tool that then selects all the different logic cells that then get laid out into that picture I just showed you. We can see for my clock, I needed 1,300 little cells. And we've got like AND gates here, and then inverters, muxes, all the super basic building blocks. Here's the flip-flops, those store 1 bit of data. And then as an example of what that actually looks like, over here, I've got the thing that actually generates the VGA synchronization. So before I started doing FPGA and video stuff, I always thought that video is quite magic, but actually VGA is pretty straightforward. You have essentially 2 counters, a horizontal counter and a vertical counter, and you make them count up in pixels. There we go, +1, +1. And then you've got to have these synchronization pulses that happen at the correct time. And then by changing the voltages on the color lines, you can get different colors. One thing that's quite interesting is probably a lot of people watching this used to doing like a bit of firmware, a bit of Arduino stuff. And in that case, you've got the machine that's already been made for you, and you're writing firmware that runs on the machine. But with FPGA and ASIC chip design, you're designing the machine. So this looks a bit like C, but actually it's telling Yosis, I need a counter that can count up to this, and it builds an actual physical counter made out of those cells that we saw here and that I showed you on the actual GDS layout here. So like we could go in and find one of these cells. This one is an AND cell. Now, because we had to wait a year, we sent this off and we had to wait a year. So obviously you want to, one of the nice things about developing firmware is you've got this like quick iteration, you know, that's something that's happened that's really great in the kind of the embedded community, is that quick turnaround. If you have to wait for a year to get something back, which did take a long time because there were bumps in the road, some serious bumps we faced, you definitely want to get stuff to work. So the last thing I just wanted to show was, if I do this, it runs a simulation of that same clock by using my CPU on my computer to pretend to be that logic and checking that it all works. And then you can see that the thing that we actually end up with the chips that came back after a year of that design process matched up. So I'm a very happy boy. I really didn't. Yeah, I didn't have. We got news in the middle of the year that there was a serious problem, and I didn't actually think anything was going to work. So I was very happy that we got stuff back and it worked.
One question: how do you achieve like analog voltage? Can you do like some analog magic inside of the CPU, or do you have like a resistor ladder outside over there?
Yeah, so for this project, it's all digital inside, and I use this what's it called, an R2R DAC,
Yeah,
where you have like a couple of
resistor ladder,
yeah, resistor ladder, yeah, and this is 6 bits color, so I've only got 6 wires coming out, and they connect to 6 resistors. You can do the analog in the chip as well. That's kind of one of the nice things, like compared an ASIC advantage over an FPGA is you could put a radio and an A to D and a D to A in the same chip as the digital stuff. But that's almost a whole other world. So I kept my focus on the digital stuff.
So Christian in the chat is asking on which level does this simulation work? Does it simulate individual transistors, or is it interpreting the Verilog or something else?
Yeah, good question. There's like lots of different types of simulation. You can simulate on the electrical level if you want to. So you actually model all the transistors and the gate thresholds and all the analog voltages, but that is incredibly CPU consuming. So you might have to wait 10 minutes to render 1 frame of video or longer. So then you can also do the thing where you say, okay, well, instead of simulating a transistor, let's just assume the transistors are perfect and they switch like with no delay and there's no analog voltage. that simulates a lot quicker. And then you can do other tricks where you basically convert the digital logic into C, and then you run the C, and then that runs a lot faster. And that's what's happening here. So this can run in real time because of all these tricks. But if you're serious about wanting to make sure your chip works, you should also do something called a gate level simulation, which is where you're simulating down at the level of the gates to check that if you say forget to connect a wire, you've got like a floating wire. It could be 1 or it could be 0, and that could totally ruin your design. And you would never see that with a simulation that is assuming that there can't be any floating wires, whereas an electrical simulation would pick that up.
So what was the problem that you discovered half a year later, or what you mentioned before?
Yes. What's a good way to summarize this? If people are like interested to learn further, I've got my YouTube channel and I kind of cover this in various videos, so check that out. It's called the Zero to ASIC course. I've lost the correct window, so I'm just gonna. That's the YouTube. Yeah, I think that's correct. Yeah. So let's just go back to the this view. I've got my camera right in the way of the screen. This is quite a small design. It's only 220 microns, and this process is 20 years old. It's free, by the way. So this is like, if anyone's really interested, Google are sponsoring this. So if your design is open source, they will cover the cost. So it would cost you like $5,000 or $10,000, but it's free if your design is open source. If we zoom down to the level of a transistor, that's what this pink line is here. That's the gate of a MOSFET, and I measure that. That's 160 nanometers.
Oh, wow, okay.
150 nanometers. And this process is called Sky 130, which is like a cross between 130 and 180 nanometer process from Cyprus from about 20 years ago. And so it's like what they call a hybrid process. So the gate is 150 nanometers. Now, this design is pretty simple. If we look around the outside, we've got, let me just turn on the text. It's quite, actually, it's probably a bit difficult to see because the text more. I don't know how to make it bigger, but that's one of the color channels out. That's a reset. That's another color. That's another color. These pins I'm looking for down the side. Another color. The buttons to adjust things, and here's the clock. Now, when you're writing firmware on an Arduino, say, someone has already made sure that everything is working correctly and the clock goes to everywhere at the right time. When you're doing an ASIC, all this logic, anything with it that is using a register to store a bit of information using a flip-flop, say, they all have to get the clock at the right time. If one gets the clock a bit later than the other, you might miss a bit of data. So one thing that's very important is this clock network, so we can follow this trace in and see where it goes to, and it's going to get distributed to all the flip-flops. And after you've done the layout, you need to run a check that basically says, okay, the clock network's not perfect. This flip-flop's going to get the clock 20 picoseconds before this one, but it's close enough, not a problem. But one of the problems we had with MPW1, which was the first sponsored Google shuttle, was the tools that were meant to do the clock network were not configured correctly. So the time was like a nanosecond, like 1,000 picoseconds, so way too big. And then the other tool that is meant to check the timing of the clock network was it's so funny looking back on it now, was also set up badly. So it was like, yeah, cool, the clock network is fine, no worries, because it was configured badly. So then when we got the chips back, we realized that the actually I don't have it here, but if the picture that I had behind me, actually I can load it up. It's a longer load, but I can load the entire layout. Where is it? That's just the part that has my designs on it, but this is the whole chip. Longer load. It's about 300 megabyte compressed file.
Moo.
There you go. So now at the bottom, we've got the RISC-V CPU and 2 kilobytes of SRAM. So this is giving us a little CPU we can run some firmware on, and its job is to configure all the IOs to be inputs or outputs around the corner, around the edges. We've got these little blocks of logic. They tell the IO pins whether to be ins or outs or highs or lows or whatever, analogs. And this is quite a wide design compared to mine. So if we measure this one, it's 2,000 nanometers, so about 2 millimeters. And the clock network meant that flip-flops over here were getting their clock way late than the ones over here, and the CPU is basically a mess. It doesn't work. Whereas my designs are quite small and they do work. And Sylvain Minot, who goes under the handle of TNT, did some amazing bring-up work on here by basically using an FPGA to control voltage levels, and by putting the core voltage at 1.4 volts instead of 1.8 and slowly ramping up, you can find the sweet spot for the chips. Everyone is a bit different, but at a certain point you might find that it can load 1,000 instructions of RISC-V assembly, and that's enough to configure the IO, and then the designs inside can get out. What we thought was this was always going to be broken. We'd never configure the IO, and the designs inside, while they might be working, would isolated from the outside. You couldn't talk to them. But yeah, Sylvain managed to. We go back to this little board here. You probably need to make the screen bigger to see it. I apologise about my lighting condition. I didn't think about that before the podcast, the screen. But the FPGA is attached to this top board, and it can control the voltages of all the voltage rails on here, and then it can bring them up and down and measure. It pretends to be a flash, and it checks how many flash reads the CPU can do before it crashes. And you've got to go through all the chips, do the measurement, find the right voltage range, and then load the firmware that configures the IO. And then the designs in the middle, if they're small enough, they work. And then the board underneath that is just like a bit that supplies the VGA and the buttons to adjust the time.
That's cool.
So yeah, it was ups and downs. It was an emotional roller coaster. It was we were all oh no, that months of work and year of waiting is all down the toilet. Oh well, at least I'll put some epoxy dyes. That'll be fun.
So how many hours did you spend
amazing.
with
How many hours?
Let's take the working clock. How many hours, approximately? Okay.
Well, I already had the clock as an FPGA because I was learning FPGA before this, so I had the clock as a kind of FPGA learning experience.
Okay.
So the work was to translate that into GTS, which is the Gerber, the version of the Gerber, to send to the factory. I'd say it's. And doing it for the first time with the first open source tools. So this is also the massive thing, is that before this, I would have had to have paid $100,000 for the tools. This is the crazy thing. This is the thing that is opening up. It's now maybe in 5 years' time, half the guests on this show will be showing chips that they use, custom chips that they're using in their own projects. Who knows?
It's a bit time consuming, but other than that.
We had to wait for a year, but in the future, hopefully we'll be down to 4 months. That's industry standard, 4 months. You send off your design, you get the chips back in 4 months.
So my next video in 3 years.
Well, I've been sending. I'm just about to send off my 5th chip. So I've got a full pipeline, and the chips they come back when they come back.
And basically, Google pays for it, only the software.
Everything is free, so it's open source tools. So that's a big thing. Open source PDK. So that's the library from the factory. Normally, you have to sign an NDA, and I wouldn't be able to show you this picture that I showed you before, because I would have had to assign an NDA for it, but because I didn't, because it's open source, I could show you all the way down to the transistors, and that's new. That's interesting.
But how about the production line? Getting the chips, and you need to pay for that, of course.
No, that's covered by Google. So every 3 months they run a free shuttle, and there's space for 40 designs on that shuttle. And your design just has to be open source to qualify.
That's cool.
So what does shuttle mean? It's your design is this part on this connected to this RISC-V, and every design is put on this die, or?
Yeah, so a wafer, so the big round wafer with all the dies on it, this expensive part that you have to pay up front is the 40 masks that you use to build up the layers to build the chip. And because the masks right at the bottom have to have feature sizes in the hundreds of nanometers, as we've just seen, they're extremely expensive. So a full mask set for this process is about $200,000. And this is an old process. So if you're looking at like cutting edge stuff, it's millions of dollars for a mask set. But once that mask set is done, then the wafers are very, very cheap. So that's why people do this stuff for volume. And what a shuttle is no one wants, if you're doing a prototype and you're doing a development, no one wants to pay 200 grand to see that they made a mistake with the clock network and their chip didn't work. So instead you find 39 other people to split the cost with, and you get 1/40th of the wafer. And then you run a set of 20 wafers and everyone gets 500 chips back or 400 chips back, but you only pay 10 grand for the privilege. And in this case, because Google are covering the whole, they do 20 odd wafers once every 3 months, and you just need to apply and get your design in. Just apply. It's as easy as that.
It's the similarities to how PCBs got so cheap and available are striking.
Yeah, exactly. Yeah.
PCB pool.
Where's who's going to do the OSH Park of ASICs? And that's kind of something that I've been working on. So most people who've done the shuttle so far just put one design in. But when I put my VGA clock in, I was like, it's so empty. So I put in 4 of my designs and got 4 friends to put 4 of their designs in, and there's still loads of space. Okay. And then when I made my course, the 0 to ASIC course, to show people how to do this. I take 16 designs and I put them all in this space. So now I get my 400 chips back, and then I split them between everybody.
That
Have you
sounds like
published that course yet?
What's that?
Have you published that course?
Yeah, it's been going for a year now.
Okay.
It sounds like a great community project, since it's like intimidating if you think you have to design all the stuff like the GPIO configuration, the RISC-V CPU, and so on. All that stuff that you already figured out and made your experience with. That's like really intimidating to learn. But if you would say, okay, this is now open source, and maybe we can make it a community project such that some people from the community just hop on and say, okay, I have this this file, this design, can you put, or let's put it all together and we can switch the designs. That sounds like more manageable than that everyone has to learn all this stuff. So
and Mark, could you make us all like the same size? I feel a bit weird being the only big one. So, and what people are doing is, as they're testing designs, we're like building a library of like open source blocks. So what will be ideal is, if you want a chip to do a certain thing, you can like grab this block from here, this ADC from here, this WS2812 driver. That's another little design that I taped out on MPW1, was a WS2812 driver, and then connect it to a RISC-V chip, and then send it off and get your chips back.
That's cool.
So definitely, I think the open source tools are a long way behind the industry standard tools. But one thing that open source is great for is the community and the sharing of knowledge, the sharing of libraries. And I think the thing that I'm most excited about is once 10 or 100 times more people can have access to designing chips, what will they make?
Yeah.
What flavor of open source is it?
Well, the software is That's a good
No, I
question,
mean the
actually.
design. So if Google pays for that, what is it like? Non-commercial? Is it attribution?
I use
Is it
Apache
public
2.
domain?
That's the recommended one.
Okay.
Yeah. But it's a great question, actually. It's something that I raised with the OSH, because I have my ASIC clock is an open source hardware design down to the ASIC level. And I said to them, we don't really have a license that covers down to the ASIC level. We've got licenses that covers like PCBs who cover licenses that got firmware. Firmware is, some stuff is easier or different to share than others. So do we need a new version of open source licenses for chips? I don't know. I think it's a really valid question. I don't have the answer for it.
I don't know. For everything there's a first, right? So
Yeah.
make your license.
It's a very interesting world to get involved with. And there's a lot of need for help with the open source tooling infrastructure, which is still at a very early stage. So
Okay, man. Thanks for sharing. That's
make your chips
very
today.
nice to see. I'm definitely going to look into the course. I want my own chip on the wall too.
Sign up for the mailing list, and I'll give you a discount.
It doesn't even need to work. I want a chip on the wall.
Well, I'll send you one that doesn't work.
I'm gonna make a 5 timer.
Yeah.
Okay.
I didn't know when to stop.
Matthias, your turn.
I'm gonna make a design that just says Google paid for this, and it's just you can read it in the file. Google paid for this. It doesn't do anything, but Google paid for it.
I think now that Matt showed off his ASIC, there is nothing else that comes after that.
I'm also sorry. I think I went too long as well. So
no worries.
Apologies.
It was riveting. Cool. Okay.
I had a good idea.
I'm often on MakerCast recently. So, but I have quite a few projects. So this last month, we did some streams, and I don't know if I showed this already, but I can maybe share also my screen. Share to just start with here. Don't show share. Which one do I show? Share this one. Okay. I'm not sure. Okay. Can you share the screen, please?
Sure.
Okay. So first of all, we had like this DHCP sniffer, and basically I converted it to a Node-RED code. I just pasted the complete C code and replaced int with let, and it worked right away. And after that, since we want everything in Node-RED, and I have we used one of these portable Bluetooth printers to print the IP before. Now I connected the printer via USB, the Perry page it was, I think, or no, the other one. So some of those work with USB, some not, and with Raspberry Pi it actually works like a printer. So we just developed like simple stuff. Wait a second, where we actually can print PT212. We can basically generate the bytecodes to print even graphics, or string to printer. Print to payload, which basically sends. Where is it? Okay. However, it works, so we can print with the small printer even from Node-RED on Raspberry Pi, which is really cool. Was a small project. One other thing that we did on the, so this is on the trash. I can maybe show that. So this was the last one-day challenge, was VGA oscilloscope, and I will just share a short clip maybe. So this was like this is an ESP32S2 dead bug with 0.5 millimeter wire, and I even soldered on a USB connector to that. And what it did, it actually worked, and it transmitted to one of my VGA boards, right? And
So
that's actually an oscilloscope.
7 hours means that's 3 in the morning?
Yeah, something like that. So, so this dead bug has a probe connected, oscilloscope probe, and there you can see on the bottom there's like my 6 VGA ESP board, and it basically displays the analog voltage. I think it's communicating over UDP. Yeah, that was quite cool project. We need to follow up on that. And then, since maybe you saw in the background, my LED wall is dying, so I have to replace a few things. So we did a repair stream as well, and I fixed one of my screens, and that I only replaced caps and the status LED with a pink LED, which was cool. But we didn't fix the complete LED wall. Another thing that I will show also here, okay, I can stop that, is maybe I released, finally, I showed off so many times on so many streams, so I will keep it just short to show, this is Shader Toy, and you can basically run like shaders on the graphics card within the browser and write code. So I released the video on the phased arrays, which is quite well received by the people, and I just made it so the only input that you can do from user interface is with the mouse when you click. So X direction is the phase shift of the 40 kilohertz wave, and Y direction is the count of sources. So you can actually, it's linked beneath the video, and you can just check how phase arrays. So this is like 2 sources phased array, and if I move it up, it quite quickly gets like, I think it's 100, and it's simulating that in real time, which is really cool. That only runs that fast on GPUs. So
Shader Toy looks so cool.
Yeah, Shader Toy is really cool. If you visit the site, it's like there's so many cool things that are rendered like real time in just a shader without any triangles or models or whatever. So I think this is all that I wanted to share there. And since this was like, I know, maybe you can make me like bigger on the screen. So I will show a few boards. Yeah, you can do. Okay, so this is like my first prototype of the. You can see already one wire broke already. So this is my transmitter array. So I was able to like do beamforming, and with this receiver I was able to like scan, make like a sonar and scan the area in front of that array. But it's already like it's a ton of wires, and it's quite janky. So I even lost like here. This is just like my amplifier. So after I released the video, I spent a week to design a few new boards, because I want to make this was the driver. So this is the transmitter version, and now I'm doing a receiver version. So I will just send one pulse in all directions at once, and then use fast ADCs to receive via the array the echoes that are returning, and analyze them and convert them to an image. So this is the plan. I didn't test yet, and I designed a few boards. So first of all, this I soldered it today and yesterday because I received like 1 week. This is the board design. This is an ESP32S2. I have also an S3 version, but it's not supported by Arduino yet. It's in IDF. I will show another design for that. And basically, okay, I can unplug. So it supports like this board, since the S2 and S3 have more GPIOs that can be controlled. I can directly connect 2 arrays, so 16 like lines. I could do more, but I wanted to have like the DAX here and JTAG and some other stuff. So we could do like maybe 3 arrays, so 24-bit. And now I'm using IDC connectors, which is way more convenient. So you can basically make even like the cables, you can make them the length you need them at the end. And this is like my first test. So this is the receiver array. Let's start with the ultrasonic transducers or receivers in this case. There's like this analog signal is going into an amplifier board, which has quite a lot of trimmers on that, because I wasn't sure yet which values to take for this. These are like standard op amps to amplify. Like I need a bias and then some amplification. I didn't know exactly what the values to take there, so I made the design with just the trimmers, and I can adjust that, and at the end I can measure which values to permanently put there in. So the signal, the weak signal here, which is like in millivolt range, will be amplified to 3.3 volt levels. And here, this is my ADC board. And since chip shortage is so bad, I had to use BGA ADCs. They are like 6-pin BGA ADCs, and the ADCs are smaller than 06, 03 caps and resistors. So in between the 2 rows here, you can maybe, I don't know if you can see that.
Yeah, I can see them. It's amazing commitment.
So I did this board like 3 hours ago. So I wasn't able to test it, but I inspected it under the microscope, and it seems it reflowed correctly on this Miniware.
Did you do it on a hot plate?
Okay. Yeah, hot plate. I have a reflow oven, but I used the hot plate to.
No, you need a Röntgen machine.
No, I don't need it, because on this ADC it's only 6 pins, so it's 2 rows. So
you can see it all from the outside. Yeah.
Oh no, it's 8 pins. Sorry, 8 pins, and you have only 2 rows, and you can inspect from both sides and see if it's connected to the board. So this is even a challenge for the PCB fab, since I use the express service, which usually only supports, like the quick service only supports pin pitch of 0.4 millimeters, and this is smaller pin pitch. But I ordered anyways, and it actually was like on the edge. It was okay, and it worked. So the solder mask and everything was perfectly like aligned to work. So yeah, so these are the ADCs, and they are able to sample in 12-bit at 3 mega samples. So quite fast. That's why I took.
Just one other geeky question. Did you use paste, or did you just use flux for the BGAs?
So my stencil has like really teeny tiny holes for the BGA, and then so I pasted it, and then I used the Q-tip to take it away, and just used some BGA flux. But I put like a proper amount of flux there, and then when I checked on the microscope and wanted to place the IC, it was way too much. It's like you just need a teeny tiny like drop of flux, and then drag it over all the places on the board. That's way enough. It just needs to stick there, and that's all. So I don't know if it works, so I'm curious to test it in the next days. And yeah, so this ADC, it's using like a serial output, but I will use it with I2S basically, and use the clock as the serial clock and read 8 channels parallel. So we are able to just ingest all the ADC data at once and then decode it. So we need just to unscramble the bits to get the values there. So it should be like 3 mega samples, 8 channels, simultaneous stuff, and it can do even like two arrays at once, which is cool. And it can also like be used with the old ones since they're pin compatible. It isn't an IDC connector, but I use the same pinout to connect directly to the cool board there. So this is what I did today, and I also did. Oh, maybe I can show it. This board I saw that I made 3, and this one worked right away, and one had a diode flipped, so it didn't connect. But I was able to program it, and it has a pink LED. So I uploaded it.
Can you show the backside again?
It works. Okay, so pink LED here. I was able to program it with Arduino, but I have also made an this is a simple ESP32S3 board. I saw that today as well. It's not supported with officially like release with the Arduino, but yeah, I had to uninstall the old IDF because it wouldn't work with the programmer and whatnot. And now with the version 4.4, S3s are supported, and I was able also to upload a Blink program. So this is an S3 with 2 max PS RAM internally, and it's working. So I made a simple version which fits on a breadboard with extra rows, and where you have every pin available that's not USB, because you don't need like D+ and D- on your breadboard. So I made this to debug stuff, and yeah, I think that's what's coming currently. Is this all? Yeah, I think I'm done.
Just in time, that's good.
I had another geeky question for you, which I apologize if you explained it in the video, but I was thinking that the synchronization of the pulse is going to be crucial for getting a good image, and I was wondering, like, how hard was it to get that level of timing synchronization from the ESP? Like, did you have to do any special tricks to get that?
Okay, so I must admit it's not perfect. So I wanted to use like parallel I2S for that, but I didn't code that yet. So I used.
So that'd be a way of like using a hardware peripheral on the ESP to kind of.
Yeah. So I would just fill SRAM with like the phase shifted bits, and it would basically output it without any interruption.
DMA or something.
Yeah, over DMA. But what I did instead to like be quickly done with that, because I didn't spend much on the code, it was enough, but I used like a separate task, which was bound to one of the cores with a high priority, and I used then the native ESP32 registers to set the pins at once, like on like old Atmel would be like port A, port B,
Write
and
the
so
whole
on.
register at once.
So I write them all at once, and I time it with the clock counter. So the ESP has an internal clock counter, and it's like a 32-bit value. And I basically do the timing with that. I have a loop that waits for the right clock, and from then I just set the pins and wait again, and so on. So it's
You have
very
to do
crude.
a little bit of like fancy dancing to get it to work, but not too bad.
Yeah, I just started with digital write and then like a loop through the array. So like this physical solenoids thing on the Arduino works like that. It's just a loop, so it's quick enough. And the ESP32 is also quick enough to do that as well. With like, I think there's like on the it's maybe too geeky, but the ESP32, since it's dual core, it has to like handle critical sections and so on. So changing the pin mode or writing the pin has some of overhead. So using like digital write is a little bit time consuming. It's not bad, but you would have like from pin to pin, you have a slight delay. So at the end, your phase shift will be maybe you have like a slight timing off, but it's like a small angle that you would probably not even see at the end. So yeah, but
Cool. Thanks.
no worries.
You've satisfied my inner geek, and I can tell Mark wants to move on. So.
Yeah, the code
we
is
need to
public
think of a
and it's a mess. It's a mess. You can look at it.
Publish is like much better to have.
Ship
something out
it.
there. Yeah.
I should ship
Ah.
it.
Ship it. Beta testers will fix it.
Someone in
By-
the
Thank
in the
you,
audience will give you a
Matthias.
PR to make it better.
By the way, someone in the chat was like, "Oh yeah, he also made an RFID tag with an ESP," and he probably
Oh
forgot
yeah,
already.
I forgot that. Yeah.
Okay, moving on.
Oh yeah. Oh, it's like
Thanks, Walter.
I just took. So we have like this 125 kilohertz RFID tags, that the white cards, where you can just like old school RFID doors, you would be able to open with those cards. And what we did on the last stream is just to take the coil, only the coil, not an extra IC, connected to 2 GPIO pins of the ESP32, and all the people doubted that I'm able to like control anything or emulate an RFID card. And what I did, I keep the 2 pins as inputs, so we have like high resistance there. Basically, there is no like dampening of the 25 kilohertz signal. So usually the RFID card would respond by shorting the coil. So you have like a coupling, an inductive coupling, and the RFID reader would see that and read like the ID and so on. So what I did, I kept them like as inputs, and then I just took the data of one of the no, what was it? Yeah, we are able to use like one of those inputs, just read it, and we are able to actually even see like the clock. So it was like the other end would be like floating, and one end was okay. It's confusing, but at the end, I just switched the pins that were connected to the coil. I switched them just from input to ground. So it's from input to output with both set to ground, which would like inductively couple this and drag it low. And then the signal was like in special encoding, and we are able, like we made a small code that we are able just to output any ID that we want. So this was like the last state, but it wasn't like it was too late to implement like a reader with this coil, so we would be able to just to copy a card and maybe emulate it. But this was like, okay, I wasn't prepared for that. I would love to show it, but maybe I show it next time. It's cool. You just need a coil, and an ESP or any Arduino basically would work as well to emulate an RFID card of 125 kilohertz.
It sounds like the next thing Hack 5 would sell.
What?
It sounds like the next thing Hack 5 would sell.
I don't know Hack 5.
Oh,
Okay.
I think they did something with the ATtiny ones.
Yeah, there is an ATtiny version of that. So, but it
was
uses
it,
assembler,
Semicon?
and it's able to run from the
LimeWire.
energy that's provided by this RFID itself. The ESP32 would never boot from that.
Prime.
Okay, guys.
Okay,
let's,
sorry. Next
because
one.
of the time, we need to move on a bit. Thank you, Matthias. Deshipu, your turn.
Okay. Do we still have time for the quiz?
Oh,
No,
we'll make time.
I wouldn't miss that.
I'll just give up my time. We'll just go straight to the quiz after you.
Oh no!
No,
That's
no, no,
wrong.
No.
No, we can't do that. So yeah, half a decade ago, about 5 years, in the time when you could still buy any chip you wanted, there was this guy on Hackaday.io that made this device.
Oh no, that's me.
Yeah, and he made me really, really jealous of this. So I started so of course when you look at projects on Hackaday.io, it's like, oh, that's really cool, and then you start looking into details, and you go, no, this is wrong. I would do it completely different. And some people even write that in the comments. But yeah, I decided, okay, I'm going to do the same thing but properly. And for the next 3 years, I basically made about 50 prototypes of game consoles, like tiny game consoles that you can program yourself to make simple games. And one of the last ones, it's last one because chip shortage came and I kind of stopped doing that. Is this one. That's the Pew M4. It has the SAMD51 on it and some nice color screen. And you program it with CircuitPython, which is super convenient because you just tell it where to put sprites, and it's just a USB drive, so just need a text editor. But this it has ESP32, so it has Wi-Fi on it. This is just a game console, nothing else. And I kind of felt like it's still like my mission is not still finished. I need to do something. But the problem is all my libraries are for CircuitPython, and it doesn't work on ESP32 because you really need USB to make this convenient thing where you just use a editor and just change the files on the disk without any special software, without flashing and so on. But recently there came out this little board that's the Lovin S2 Mini, and it's quite nice because it has the ESP32 S2, but it's backward compatible with the ESP32 D1 Mini. So the external row of pins is like on the D1 Mini, and the internal one are just some extra pins that you can use. So, and more importantly, it has really USB. So there is CircuitPython running on it. And I for a while I planned to finally make a game console that has Wi-Fi on it, even though I don't use it for anything. And I also wanted to have like a little bit bigger screen, because I don't know, somehow all the game consoles you can get have these really tiny screens that it's, if you put them against like even the original Game Boy, they look like super tiny next to it. So I found those screens, and this is the Ili 4391 screen. So this is the default 320 by 240 screen, but it's like 3.5 inch. So I'm really proud I found those, and I decided, okay, I need to make a version of my console with that. And it has this ESP32S2 basically chip on it, so you can use Wi-Fi now with my games. I put some games on it so you can see it. Hopefully, it takes a while to load, but yeah. Then
What's the price of the display, by the way?
Sorry, about
What's the
$10.
price? Okay.
About $10, so it's not too bad. It's more than like the one I used here is about $3, so much cheaper.
Are those?
So you're roughly at $20. Oh.
So the thing here, I'm also using 2x2 pixels. So because my games were written for this big display that is 128, this one is 320. So I could double the pixels basically to have really nice big pixels. You can maybe it will focus, maybe not. Yeah, you would have to see it. Oh.
Yeah, we can see it. That's clear.
Yeah, and this is a simple platformer. Oh, I just died. Anyways. So yeah, I also made a second version. So the nice thing with this that I was particularly proud of is this acrylic case, which is basically laser cut. So it's just 2 layers of laser cut acrylic, and the buttons are those really tiny buttons with pieces of acrylic glued on top of them. So I want to do a similar case for this as well. I designed it so that you can have 2 pieces of laser cut acrylic here and then a transparent piece on the top. I'm not quite happy with the batteries like this. I'm also thinking about doing a version with inline batteries. That could be a bit more convenient, and then I can move the chip itself to the middle of the board. Oh, and by the way, I also soldered some headers on it, so you can actually put the D1 Mini shields on it. So if you have additional sensors you would like to use in your game, for instance, accelerometer, maybe LED, like now pixel with backlight for your game, changing color and stuff like that, you can easily do that. All the pins on the outside are unused by the console, so there is no conflict with any of the other shields you might want to connect to it. The Wi-Fi. Right now, I didn't publish anything. The question is if it is open source. I didn't publish it yet. I do plan to publish it once I verify that everything is fine. I put everything on Hackaday.io, so it's going to be there. Yeah, one problem potentially is that the Wi-Fi strength is probably not going to be great, because there is this ground field just below the antenna. And if I move, I actually can remove it because there is nothing important on this piece of the board. Like it's empty on the other side, so I could remove it. I didn't do it because then it would look bad. But if I have a case, then it doesn't matter. I could, modify. This is the first prototype. The thing is, if I move it to the middle, this display has metal on the back, so that would be even worse.
You can maybe put some kind of silkscreen art in front where the block would be that actually would cover it somehow, like.
Yeah, I can.
Yeah.
The thing is that the display itself is metal on the back.
Yeah, no, so, I mean if we could keep it on the right side, and then you would remove the ground layer. I would just put some art there so it doesn't look like.
So the thing is, here I soldered it directly to the board, so it's flat on the board, and that might be problematic. Originally, I put it with some headers, so then it's raised from the board. And then it should be fine. So probably I will stick with this. Then I need some case for the back because it's right where you put your hand. That's also a problem. There is basically no good position for it.
What kind of interface is used for the display? Is it like a flat flex cable or?
Interesting thing. So I started with this version that has, you can see, a lot of connectors, and that's a parallel 16-bit interface. So you can really do fast refresh, and it clocks at 40 megahertz. So you can really push pixels fast on it. The problem is, so originally I didn't actually want to use the ESP32S2. I wanted to use the Raspberry Pi Pico, the RP2040. And I was counting on using the PIO for pushing the pixels to it. And I was counting that the higher resolution of the display would be offset by the fact that I have this super wide pulse and that I can use PIO for it. But I did some experiments with that, and it turns out that the overhead I get from using display I/O on CircuitPython negates that. So eventually I used much from the same producer, just different serial number of the part, the same display but with SPI interface. So the same old boring thing, and because this is ESP32 that has like 80 megahertz SPI clock, it's still quite fast, and I can then use Dave, don't kiss the duck. You can use then the faster clock, and that, and I can use then my own sprite library instead of display I/O in CircuitPython, which is also much faster. So that's that. Quickly now. I also mentioned that I recently, like for the last 2 years, I'm diving deep into keyboards. This is my endgame keyboard that I'm using for work, that I came up with after a lot of different trial and error. I started with a full keyboard, then like 10 keyless, then split, then this one. And it turns out the less keys a keyboard has, the more convenient it is, and the less your hands have to move around. So I got some wrist pain and so on, so this helped a lot. I eventually added the arrows here, and added the modifier keys as separate keys, but the base layout is the 36 key layout. But then I got into that community, and there are other people making keyboards, and then they insidiously inspire you to making more keyboards. So I saw this video by Ben Valak of his card keyboard, which is basically the credit card sized split keyboard that he made. And I thought, oh, that looks pretty nice. I want to make something similar. So I made this inspired by his. It's not split like two-piece split keyboard like his. It's connected. But it has the same basic layout. The problem is you barely can reach this thumb key with your thumb. It's just like the very end of your thumb that reaches it. But it's usable. So it's nice for travel, I suppose. And it's been fun to design because this is the PCB for it. It's only 1/2 because you have to order more PCBs, so it flips. So you have 2 of them, and then you use some bent.
Yeah, I wondered what the jumpers in the middle were for. I thought that.
Yeah, that's just bent male headers to connect the 2 halves. And because the switch footprint is asymmetrical, you can have a pin on each side that connects to the different pin on the microcontroller. So depending on which side you use, you can basically there are no clampers in here to select which side you are using. It's just just works.
It's super cool.
And I also had fun with the clouds. They actually line up. Yeah, Usagi, I was thinking about making it fold, and I could do that if I used like a ribbon cable in here, but I would have to design a mechanical hinge for it to make it like properly robust, and that's beyond my skills, so I left it as one piece. And then the unexpected maker, Sion from Australia, released his S3, ESP S3 boards, and those are the first ESP32 chips that have both USB and Bluetooth. So I thought, okay, maybe we could make a keyboard with that. So I decided. So this is called the Vegemite sandwich because it makes a sandwich if you put it together. And there are a couple of very experimental things in here. So of course the ESP32S2, the tiny S3, not S2, S3. The tiny S3 thing. That's one thing. Second thing is for the first time, instead of soldering the keys into the board, I used sockets. So you can actually remove the switches. And that's why I made them like rectangular with all the switches in there. You can experiment with different layouts.
Wow.
So you can put this key in here instead.
I hate you.
For instance. And then you can also replace the switches with different, clicky, linear,
emojis,
tactile, and whatever. So you can do a lot of experimenting this way. And I made it both. Right now it's wired. This is the TRRS cable to connect the 2 halves, because right now it's programmed to work as a wired keyboard, because there is still no support for BLE service for this chip, at least in CircuitPython that I'm using. So by the way, you also can edit the layout of the keyboard by just editing a text file on the drive that appears when you connect it while you hold the key. So you can change your layouts as you wish live without any special tools.
The nerds will love that.
Right. So, but this is work in progress. When I started with this, I couldn't even get to work the two halves because they communicate through serial, and the serial communication was broken on that version of IDF. So, yeah, it's very much a bleeding edge thing. I'm going to let it sit a bit for the BLE, for someone else to fix the BLE, and then I can make the wireless keyboard. So, there is one more thing. When it's a wireless, you need batteries. And I've heard that ESP32 is not that great for low power use. I mean, it's great in deep sleep, but not when you have to use it as a keyboard. So I decided to use my favorite batteries. So basically, you put this in here. I need to solder it to use it in wireless mode, and the battery looks like this. So I think that should last for at least a day with the ESP32, if I'm lucky. And the additional effect of that is that you have tenting with your keyboard. So you have this bump, so the keyboard is not flat on your desk, but at an angle, which is good for your wrists as well. That's that. I can also show some pink LEDs. That's an old project that doesn't work, but they are pink.
Cool.
Yeah, I have one thing in progress that Dave already knows about because I put it on Academia.
Do it next time. Sorry.
But I will show it next time when it works. And,
yeah. But I want to see it, but I think we're running out a bit of time.
So sorry.
That's not your fault. It's our fault. But yeah.
Yeah, doesn't matter.
Okay, thank you.
Thank you. So I will just keep this as short as possible. I will just skip a few items, which is okay. You can always do it next time. I'm working on a new spectrometer, but not like this one, but a digital version. I have two displays, the same like your like the deshipu was using in his games, only bigger size, and two of those are going to be in one panel. It's going to be a replacement for a VEU meter. They used to be in the old band recorders, and it's actually an open source project. It's somebody else already made it, but what I'm going to do is I'm going to port it to the ESP32 because the original is done on a Tinsy, and I'm not too fond of that. Not that they're bad, but I'm just a big ESP32 fan. So that's one thing I'm working on. I'm not going to show it to save some time. I'm going to talk about a project, a long-time project I'm going to work on, and for that I will start a video. Let's see if this works.
Quick drive arrangement for the primary coil.
This is Meet Parker Edmondson.
Okay, so I'm using the equi-drive arrangement for the primary coil or tank circuit, and so I have 5 14 nanofarad capacitors on this side and 5 14 nanofarad capacitors on that side of the primary coil. Here are the ratings of the transformer. There are almost 18 turns on the secondary coil and 100 turns on the extra coil. The sphere on the top is 20 inches in diameter.
I know, no big deal. He just loves to play with electricity. Wrong. This is what happened when he started it up. He made the NBC News. Was it safe what he did? Well, I don't know. Let's not judge about that for now. He also published a video about using his distribution transformer. Take a look at that.
Ballasting my 50 kilovolt amp pole transformer with a 60 amp welder on the primary to test it.
Well, it's not something I would have done next to a swimming pool, but you know, Parker, you're killing it. You're doing what we all want to do. You're living the inventor's dream. Keep it up and keep it safe. So basically, why I'm showing this, there's a reason. I asked his permission, by the way. I contacted him today if it was okay to show the video, and he agreed. So this is his garden, and he has this. He made his big Tesla coil. It's he's trying to prove that Tesla was right in his wireless energy project. Let's not get into that, but what he does, he every time he has projects and in the forum we're looking, is he still alive? Because what he did today, it's it's so unsafe, or maybe it's not. I mean, all Electro Boom, he does unsafe things, but at least there we know it's a show, and here it's just well, a guy is doing what he wants to do. He's being a scientist, and probably this is how we all started. But it got me thinking, and it's probably something that more makers deal with, and that's safety, because it's something we don't like to talk about, basically, unless it's for your profession. And for my profession, I asked you guys all in the beginning, what do you do? And I didn't mention mine. I just realized I actually work in university, and part of my job is safety for electrical devices, mostly medical safety. And then sometimes I see people building an ECG amplifier, put it on YouTube, and well, safety's down the drain. And that's basically what I just saw in the video. And the reason I'm sharing this is I'm going to start an awareness project for makers, but it's not going to be me handing out some rules like how to work safely, but I'm going to make it how to say this, an experience. I'm going to do some research and make some videos about it and show the people what's happening and why something is safe and why it's not. It's not going to be me schooling people. That's not the idea. Let me just share another. Oh, I have to share my screen. That's possible, right? Because I'm sure everyone sitting here probably in life one time or another got electrocuted by accident touching the main outlet. I don't think
coincidentally also near a pool.
Maybe. Let me just share the screen. This one. And one of the things I'm going to start with, and this is probably the most challenging, the reason why when you got shocked you survived and some other people didn't, well, there are many factors, but one important factor has to do with the heart rate. You're looking at a picture of an ECG, and imagine this repeats every 60 seconds, every second, like 60 times a minute, approximately, in this rhythm, and it repeats. But there's a cycle, and this is this part, that you're very vulnerable for electricity. That if you were to get a shock exactly at that period, there's a big chance your heart will stop or start to fibrillate. And we're all just very lucky that it happened outside of that window that we live and tell. And what I'm going to start with is, together with someone at work, we're going a cardiologist. We're going to look at this, and I'm actually going to build an ECG amplifier to find that window where to get electrocuted. And that's the challenging part, because I don't want to build something.
Your shock machine.
Yeah, exactly. That's not what you want to build. You don't want to build something open source and put it out here and say, "Go experiment. This can kill you." Success rate guaranteed. So that's going to be the challenging part for how I'm going to build this and prove that it works.
So it doesn't find the heart rate. Does it find the heart rate that's safe, or does it find the heart rate where it's definitely kills you?
Like, make it just so there is like the amplitude is basically zero at this vulnerable.
Yeah, but then it doesn't prove it. I need to prove. What I'm probably going to do is make an ECG amplifier that will just light up a LED at the moment it's there. Like if you get electrocuted in this very moment, don't. But I cannot try it. I like take a piece of beef and start experimenting on that. But I mean, maybe I can ask my neighbor. You have 5 minutes. But that's a challenging part. How to going to prove that without doing harm to people or animals, because that's not my intention. Of course, I could go to the laboratory at work and say, guys, this is what we want to do, and they get some lab animal, but that's not what this is about. But it's all about awareness, and by doing it this way, it will be probably a funny video that we can learn from. And the background is you're still educating people with something they normally shut their eyes for, because the last thing we want to hear when we're building is safety. I mean, when I look in my basement, it's probably not as safe as working in the office, because at the office we have the tools, and at home you're just improvising most of the time. And safety is not something that is on top of your list. Let's put it that way, and maybe it should be. So that's what this is going to be about. But enough of that. I will maybe I will have some more for that when the first video comes out. But because of time, we are going to start the quiz. Let me just share my window for that. Let me put the link once more in the comment. And then let me share the screen.
Oh, yeah. Quiz.
That's getting serious.
Quiz!
Quiz time.
Where's my quiz window? I open it already.
I have to raise my hand. What does it mean? What does it mean?
For those who are participating, and you open the link, you come to this screen, and there's a little settings here. If you click it, then you can enter a name. And you can name whatever you want.
Okay.
Oh, it says here Nick. Okay, I'll do it for Nick. And then later we can see who's the winner, maybe.
Oh.
There's another link, but we can just skip that. That's what I just showed you. Put the name. Here's the first question.
Oh.
What is the formula for calculating the resistance of a string of wire? And there are 3 formulas that might look familiar to you or not. And you can just select the answer you like and then click send. Let me give an example. You can just click this one.
I'm so
Let's say
smart.
the right answer, because that would be too easy.
I go for the one with pi in it because I think it's related to how big the wire is.
Okay.
And I've heard Z before.
Yeah, then we move on to the next question.
Ooh.
What is the resistance of a resistor with the following coloring code? And there is no extra ring for tolerance. So it's gray, red, black, and silver.
I'm
Looks like it's on fire.
colorblind.
It's the lowest
why
one because it's the one
it's
that's burning
text.
so quickly.
Okay, so I take this.
When I started learning electronics, I got like this apprenticeship, and they nearly kicked me out because I was colorblind, and that would nearly have ended my electronics career.
Okay.
Let's just measure
Answers are
everything.
coming in. I'm waiting a bit longer than the first time because more people are participating.
They're just
Whoa,
cheating.
whoa.
Just click. Continue.
I think they got all.
Ooh.
Now this one. Using electrolytic capacitors, which of the following setups will work and will not send the capacitor to the analog afterworld? So there's two capacitors and they're connected to an AC source. And number 4 is none of the above, by the way.
That's weird.
I see most people are okay. The odds are evening out.
No.
Is it normally this hard?
No.
No.
Well,
Actual questions normally.
I did
Well-
one once, and people were not happy with me.
No, you see.
Oh no, that
video.
wasn't me.
This was the one blowing the capacitor. Those were in anti-parallel. But that was not the right answer. And
What?
this is the correct answer. In
Nice.
anti-series. I always knew that it worked because I did it a very long time ago, and every time I explain to people, think I'm crazy. So I just decided to hook up two capacitors to a source and film it. This is, by the way, DC source, but the principle is the same because they have a polarity. Okay, next one. What type of USB connector is this?
There is no photo.
It's up left. It's in
up
the
in
bubble.
the top left.
Oh, that's a
This one. If you click on the photo, you can make it big, but you have to do it in your own interface.
The old
yeah,
upside
it's
down.
easy. It's labeled on the picture. It says D there.
Nice try.
For this answer, you get a D-.
This one is for bitluni.
Oh,
Put it in
no.
there because we know he's into ultrasonic at the moment. Ultrasonic effects were first discovered in 1790, but it took up to the 1940s for the first physician to use ultrasonic in medical diagnosis. In what year was the first ultrasonic technology capable of making 3D images? It's not hard at all. So what year were we capable of making 3D images with ultrasonic technology?
Okay. I never do my research, so
You're just making beautiful pictures.
yeah.
That was a nice video, by the way. Really nice.
I need to send it.
Oh wait, is this the device? Oh, I clicked the wrong button, I guess.
The answer was 1990, by the way.
Oh no!
Well, in Europe, this goes for Holland and probably for Germany and some other countries. We have color coding when it comes to wiring the house. And the new colors, most countries are blue, brown, and green, yellow. But when you renovate an old house, you might come across some different color codings. The answer is not as easy as I thought. I figured out today because it was not. The reason why they put in the new colors was to make a standard, because every country was using different colors.
I mean, I think I answered correctly for the country that isn't the country anymore, but that I was living in and buildings were built.
Yeah.
So
You mean GDR?
duh.
For us, it was always whatever is the cheapest at the moment.
Well, the funny
And it
part is,
still is. You can get people still using cables that are not up to code because they're
the
cheaper.
funny part is they changed the colors, and I don't know who thought of it, but nowadays the color for ground used to be the color for face. So if you're renovating old houses, that's nice if you mix up stuff. So when you're hanging from a power line, holding it with both hands, and the voltage is 100,000 volts and the current is 15,000 amps, why not? What will happen? Will there be no problem? Because your feet are not touching the ground like the birds. Or you might fall down, you break your legs, but you will not get electrocuted. No, you will not survive because the voltage and current will surely kill you. Or it all depends on where your hands are. How far are they apart?
It's getting tricky.
People keep changing their answers.
Oh.
The answer was the last question, because if your hands were exactly close together, then you will probably feel something, but it's not enough to electrocute you. Although when they're wide apart, it will the voltage difference will surely kill you. And of course, there are a lot of other factors you have to go, like the high voltage corona and stuff, but I didn't anticipate for that. I'm a doctor, not a bricklayer. Yeah, that's a good one. This is the
I
only
even
one
saw
can
that as a
have-
snippet.
I have no idea, I'm afraid.
Well, I'm going to show you. It was all 3 episodes. That's something with technology and makers. He was not a bricklayer, not an engineer, or not a mechanic. And many other things. He was a doctor. I think we all know this. At least if you're maybe a bit older and you used to play with this. I think in Europe and the States this was very popular. The old CB radios.
Oh, I have one up there somewhere.
Well, I still have them. And I switched them on the other day, and it's dead silent.
So that means it's free again. It's free real estate.
Yeah, that's how I'm trying to guess the answer. Like, how much bandwidth would have been allocated to CB and then divide that by 80?
Yeah. Well, the answer was 10 kilohertz.
I was too late to vote again. I was hesitating.
What?
I keep missing the vote
What
button.
processor was used in the Commodore 64 computer?
I know which one wasn't, but
Yeah.
Which
But
two?
the answer is now I'm really doubting if I was wrong or not.
You could quickly check.
Here's the answer.
What's a Commodore 65 though?
Oh,
It's an
oh,
unreleased
shoot.
prototype.
It's an upgrade. That should have been 64. You're right. But, it was close to the Atari.
I think I don't have a single answer right except for the first.
I think I was the one who had the one thing right where nobody else had it right, or I was the one that not had it right, and everyone else had it right.
I have absolutely no clue.
And now
I
I'm
have
trying
that
to see
one
if,
right.
if I can find a winner.
Are there any
You
more
have to do
questions?
it quickly
or-
before bitluni
No,
falls
this was
asleep.
the last question. There were only 10
No
questions.
Okay.
I can go for hours.
Yeah, how long did you say your stream was for the RFID thing?
That was maybe
12?
7 hours. No,
Oh.
I had 16-hour streams before. I think
Yeah.
that was the longest
cool.
one.
And you had a two-parter that was pretty intense too.
Yeah. That was. I think the two-parter was maybe 18 hours in total. Something like that.
Here it is. Let's see. Who was the winner?
Roter
So if you're the-
Fruchtwerk was the winner
if-
for sure.
If you're the winner, you have to host next time. Was that the rules?
Yeah, something
No, the
like that.
loser host, I think. bitluni! Oh, sorry.
No, not again. I was last time.
Okay.
And we have a winner.
No, the time
Who is
before.
it?
Oh wow.
Who is it? It's not on the
Unfortunately,
screen.
it's one of our guests. Because I mean, unfortunately, it would have been nice if it was in the audience.
So who is it?
was actually Dave
Fruchtwerk?
Darko.
No.
Hey!
It's
Hey, Dave!
Yay, congratulations.
Dave, congratulations! What are you doing next month?
Hosting.
Yeah.
Yeah, boy.
Okay, guys, it's been great. It's been a bit longer than anticipated, but we had an extra guest today, so it's fine. I hope you guys enjoyed, and
It
for
was
everybody
really
who's
interesting.
watching, I hope, of course, you enjoyed, and you can always look back. And if you have any questions, don't hesitate. You can always contact one of us, or you put a comment in the video, and we will see to we can answer it, or we can redirect it to the right person. And hopefully next month, we have some more exciting stuff. We don't know yet who's going to host, but we'll figure it out. Until then, I wish you all a very good night.
Bye-bye.
Bye-bye.
Bye bye.